Hello. Hopefully y'all are doing well. And I hope all of you went to a AP pre-administration session with Miss Nasser. She said tons of kids showed up on Friday, which is amazing. So thank you to all of you that did that. And if not, it's okay. Just keep watching your email for more opportunities. And if worse comes to worse, you can do it when we come back to school. You just might have to miss some class to do it. So we are going to continue on with our Taylor and Maclaurin series notes. So I'm going to kind of first start with a little recap of what we learned in the last video. So this is Taylor and Maclaurin series. Day 2. Okay. So just to recap, we can approximate any function. So it could be e to the x, could be sine x, cosine x. Those are some of the ones we did last time. We can approximate any function with a polynomial. It's kind of weird, but let me show you one, for instance, if I can get this to not be so overly bright. Let's see if I can adjust this so you can see better. Okay, so for instance, with sine x, let me make sure I'm in the right mode. Okay, the Taylor polynomial or Maclaurin polynomial that goes with that we learned in the last video is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay, and just FYI, factorial is if you go to hit the button math, and then over to PR, the probability, and then option number 4 is the exclamation point, the probability. Okay, so what I'm telling you is that this series should look like sine x. Now, the little caveat is that it will look exactly like sine x if I had infinitely many terms in this polynomial. So if I kept going, if I had plus x to the 9th over 9 factorial, minus x to the 11th over 11 factorial, and I continued that pattern forever, it would look exactly like sine x. But even with just 4 terms, you will be able to see the similarities. So here, the first thing that's going to graph is the polynomial, which may take it some time. So here it comes down. Okay. And then here's going to come sine. So notice there in the center, they are very, very, very similar, if not the same. And remember, this polynomial is centered at x equals 0, which means it's going to be the most accurate the closer you are to 0. Okay, so there's that up to the x to the 7th term. And like I said, the more terms you have, the more accurate it will be. So like, let's go ahead and add on the x to the 9th term. So plus x to the 9th over 9 factorial. I'm going to go ahead and do a couple more. So plus x to the 11th over 11 factorial. And let's just do one more. Minus x to the 13th. Hold on, that should be plus. We need to alternate there. X to the 13th over 13 factorial. Okay, so now let's see how close we get to sine, or if it's any better than the last time. So it's coming slow, but here is that polynomial. Coming in. Slow and steady here. But I think you can already see that where the last one kind of only got these middle 2 humps correct, this one it's adding more humps. So you can kind of see that the more of these terms, the wider you'll get and the closer it will be to the actual sine curve. So you can imagine that if you had infinitely many terms in your polynomial, it would look exactly like the sine curve. So look at this. Isn't that cool? So in the middle, it is very close, if not the same, as the sine graph. So that is the idea behind what we're doing with Taylor and Maclaurin polynomials. So let's get back to kind of recapping some of the formulas in our notes, and then we'll do some examples of different types of problems here. Get this set up. Okay, so remember a Taylor series. And I'm going to kind of use series and polynomial interchangeably here, because the series just is referring to our infinite polynomial. So the Taylor series, or our infinite polynomial, always has this format. F of A plus f prime of A times x minus A plus f double prime of A over 2 factorial times x minus A squared plus f triple prime of A over 3 factorial times x minus A to the third, etc., until we get to our infinite term, or our sigma notation, the sum from n equals 0 to infinity of that derivative. So f, I'm going to put in parentheses the nth derivative at a over n factorial times x minus a to the n. Okay, so in my first couple terms, you don't see the n factorial, but that's because it would be 0 factorial, which is always 1, and 1 factorial, which is also 1. So the factorial you're not seeing here. And then this first term, you're not seeing the x minus a, but that's because it would be x minus a to the 0, which is just 1. So here is how you kind of expand it out, and here will be the sigma notation. Okay, so this is a Taylor series where it can be centered anywhere. So like, say you have a problem and they give you f prime, f double prime, f triple prime at x equals 2. Then it will be centered at 2. Up to this point, we've only had ones that were centered at x equals 1. And those are called Maclaurin series. So the formula for those is super similar. It's just that instead of the a, we have a 0. So f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared, and then over 2 factorial, plus f triple prime of 0 times x cubed over 3 factorial, plus dot 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 until we get to the nth term, which would be the sum from n equals 0 to infinity of the nth derivative at 0 times x to the n over n factorial. So it's the same exact formula. We've just plugged a 0 in for a. So Maclaurin series is just a Taylor series centered at 0. And if you're wondering, like, where did this format come from? I would encourage you to go back to the last notes video and watch that first example where I gave you f prime, f double prime, and f triple prime at 0. And we started with the third derivative and we integrated all the way back up to f, and it always comes out in this format. Okay, so I would encourage you to go back and watch that first example to see why it is in this way if you're not sure. Okay, so what we're going to be doing today is using series that we know to find similar series. So we can use series we know, which you might be like thinking, I don't know any series, but there are at least 4 or 5 that you should memorize. So like the ones from pages 11 and 12. those you have to have memorized. And on the AP test, they expect you to know those as well. So those would be the series for sine, cosine, e to the x, 1 over 1 plus x, I believe. No, sorry, 1 over 1 minus x, and then the natural log of x plus 1. Those are important series to know and have memorized. Of course, I don't expect you to have them memorized quite yet, but the time is coming when you will be quizzed on that. Not the first day back, don't worry, but relatively soon. So we can use series we know to find similar series. So here is the rule. If you know the series for f of x, then there are these 4 properties you can follow. The first one is if you just multiply that function by some constant k, then the associated series would just be k times the series for f of x. So let's say you know the series for sine x and you want to figure out the series for 2 sine x. Then you would just multiply the series for sine x by 2. Okay, the next one is f of k times x. So say you multiply the x value by a constant k. Then what you would do here is you would, in your sigma notation, you would still have your nth derivative at 0, but instead of having x to the n, you would have k times x to the n, and then over n factorial. So you're going to have to multiply the individual x values by k. A couple other cool rules. If you want to find the series for the derivative of a function that you know, oops, I'm off the page. Then you can just take the derivative of the series for f of x, assuming f of x is a series that you know. And then similarly, if you want to find the series for the integral of a series that you know, then just integrate the series that you know. So the series for f of x. So we're going to do some more fun calculus stuff today, derivatives and integrals, which is always great. So I'm going to do some examples using the series that we learned last time, sine, cosine, e to the x, 1 over 1 minus x, natural log 1 plus x, and we're going to be kind of manipulating those to find some other series. So for our first example, this is example 1. Find the Maclaurin series for f of x equals the sine of 3x. Okay. So we always want to start with the series that we know. So we know the series for sine x. So I'm just going to go ahead and write that out. So the series for sine x is, and you can either write the sigma notation or the expanded version. I like to write both. So it's the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. This is something that does need to be memorized. And the expanded version is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. So I'll just put plus dot dot dot. So if I want to find sine 3x, okay, I'm going to take the series for sine, and instead of where the x is, I'm going to change it to a 3x. So I have negative 1 to the n times, so instead of x, I'm going to put 3x to the 2n plus 1 over 2n plus 1 factorial. So literally that's it. Just change the x to a 3x. And in the expanded version, do the same thing. So change every x you see to a 3x. So 3x minus 3x cubed over 3 factorial plus 3x to the 5th over 5 factorial minus 3x 7th over 7 factorial plus dot dot dot. And oftentimes, like on free response, they might ask you to, give the sigma notation and write the first 3 terms, the first 4 terms. So that's where you would want to make sure that you can do both. They would also give you a point for having the series for sine memorized, and then maybe a point for the sigma notation for sine 3x, and maybe a point for expanding. So it is vital that you have these memorized at some point. Okay, so let's look at another example using a series that we know to find a series that maybe we don't know. So how about, for example 2, same thing, find the Maclaurin series for x over 2 minus 2x. Okay, well, I'm thinking of this series that were on the previous 2 pages. The one that's the most similar is 1 over 1 minus x. So 1 over 1 minus x. Now, definitely not the same, but it's sort of similar. So let's just write out what that was from the other day. So that series is the sum from n equals 0 to infinity of x to the n. That's like our most basic, easiest Maclaurin series. Okay, which if we expand that out is just 1 plus x squared plus x cubed dot dot dot. So it's literally just the most simple polynomial you can come up with. So now we have to figure out how can I go from here to here, or vice versa. So for x over 2 minus 2x, okay, wouldn't that be equal to, let's see, if I pulled an x out from the numerator, I would have this, 1 over 2 minus 2x. And then on the bottom, I can factor out a 2. So I can factor out an x minus 2, x over 2, I'm sorry, an x on the top and a 2 on the bottom. And then on the bottom, I'm left with 1 minus x. Look, it matches, yay. Okay, so the series that I want to know, x over 2 minus 2x, is just equal to x over 2 times the series that I already know, 1 over 1 minus x. So we are going to just take that series, which is just x to the n, and we're going to multiply it by x over 2. So just like that. X over 2 times x to the n, which if you want to kind of simplify that a little bit, x times x to the n would actually be x to the n plus 1, and then it would all be over 2. You could rewrite it like this, but both would be correct. And then if we wanted to expand it out and give the first, let's say the first 3 or 4 terms, you can, there's a couple ways to expand it out, by the way. You can either actually plug in 0, 1, 2, 3, or you can take the original series and manipulate that. So I'm going to multiply each term by x over 2. So I multiply the first term by x over 2, get that. Multiply this x by x over 2, I would get x squared over 2. The next one, I would get x cubed over 2. The next one, I would get x to the 4th over 2. Do you see that? Which is the same thing you would get if you plugged in a 0 for n, you get x to the 1st over 2. Yay! If you plugged in a 1 for n, so plug in a 1 here, you would get x squared over 2. Yay! So either you can plug in the numbers to expand it, or you can manipulate the original to expand it out. Okay, let's try another one. So example 3, same direction, so the Maclaurin series 4, 1 over 1 plus x. So this is 1 over 1 minus x. I want to find 1 over 1 plus x. So there's actually a couple of ways to do this one. So one of the series that we were given was the natural log of 1 plus x, I believe. Yeah. Natural log of 1 plus x. That's one of the ones given that you should have memorized. I would say this one is the least important of the 5 to have memorized, but it is useful for this because so the natural log of 1 plus x, that series that we know from page 11, sorry, I'm being a little scatterbrained right now, is the sum from n equals 0 to infinity of -1 to the n over n plus 1 times x to the n plus 1. Okay. So expanded out, it was, let's see, x minus x squared over 2 plus x cubed over 3, so no factorials here on the bottom, minus x to the 4th over 4, etc. So that's the series. So now the question is, how do I get from this natural log of x plus, or 1 plus x, to this 1 over 1 plus x? And doesn't 1 over 1 plus x equal, to the equal sign kind of sideways, the derivative of the natural log of 1 plus x? It does, right? So when we take the derivative of natural log, it would be 1 over 1 plus x. So if I take the derivative of natural log, I would get the series that I want. So that's what I'm going to do here as well. I'm going to take the derivative of this series, of the sigma notation, or you can just take the derivative of each individual term and then write the sigma notation based off of that. So there's a couple different ways you can do this. So what I'm going to do is I'm going to take the derivative here. So remember, we're taking the derivative with respect to x. So the x here is our variable. So I'm going to bring the n plus 1 to the front. So this -1 to the n over n plus 1, that's like a constant. So just leave that there. So with these x to the n plus 1, take the derivative. So you multiply by n plus 1 times x to the, subtract 1 from the exponent. So n plus 1 minus 1 is just x to the n. This would be your derivative. So now the n plus 1's cancel, and we just get the sum from n equals 0 to infinity of -1 to the n, x to the n, or you could just write that the sum from n equals 0 to infinity of -x to the n. So you can either, I'm sorry, that shadow is terrible. You can either leave the -1 and the n separate, or you could put them together like that. So what does that expanded version look like? So here's my answer. Let me just box that up. So to expand that, plugging in the 0 for n, we would get 1. Then plug in the 1 for n, so we would get minus x. Plug in the 2, so we would get plus x squared, and then minus x cubed, etc. So there's kind of the expanded solution. So notice that the terms here are also the derivatives of each individual term here. So derivative of x is 1. The derivative of -x squared over 2 is -x. The derivative of x cubed over 3 is x squared. The derivative of -x cubed, x to the 4th over 4, I'm sorry, is x to the 3rd. So it works if you take the derivative of each individual term as well. Okay, there's an alternate way to solve this one. So, alternate method. Excuse me. Okay, so for the first way we did it by taking the derivative of the series for natural log 1 plus x. The other way is to think of 1 over 1 plus x as 1 over 1 minus negative x. Right? It seems like a small change, but now we have put this in the same format as this, the 1 over 1 minus x. So if 1 over 1 minus x, here's 1 over 1 minus negative x. So all I would have to do is take the series for 1 over 1 minus x and replace all the x's with a negative x. So the series for 1 over 1 minus x, remember, is just x to the n, okay? Which means the series for 1 over 1 minus negative x would equal the sum from n equals 0 to infinity of negative x to the n. Okay, notice this way might have actually been easier this time. That's the same exact solution I got up here when I did the derivative of the natural log of 1 plus x. So it works either way. Okay, we're going to do one more example that's going to be a little bit different than the last two. So now I'm going to actually do our first series that's not centered at x equals 0. Oh yeah, it is still going to be centered at 0, sorry. Okay, example 4. We're going to actually use our series this time to approximate a value on the function. So here's the directions. Approximate the value of the sine of 3x at x equals 1 using 4 terms of the polynomial approximation centered at x equals 0. Then approximate the value at x equals 2. So we're going to write the polynomial centered at 0. We're going to use that to approximate the function at x equals 1 and at x equals 2. So the question is, how close are those to the actual values for sine 3x at x equals 1 and x equals 2? Basically, so how good was our polynomial approximation when I just have 4 terms? Remember, the more terms you have, the more accurate it will be. So first thing we need to do is write out our series for the sine of 3x, which we already found in our first example. So remember, that was the sum from n equals 0 to infinity of negative 1 to the n times 3x to the 2n plus 1 over 2n plus 1 factorial. So that was the series. And the expanded version looks like this. 3x minus 3x cubed over 3 factorial plus 3x to the 5th over 5 factorial minus 3x to the 7th over 7 factorial. And this problem specifically asks us to use 4 terms. So 1, 2, 3, 4. Okay. So what we need to do is use the polynomial approximation to approximate the sine of 3x at x equals 1. So at x equals 1, plugging in a 1 for x here, I would have 3 minus 3 cubed over 3 factorial plus 3 to the 5th over 5 factorial minus 3 to the 7th over 7 factorial. So I'm going to actually type that in my calculator and get an answer. So I have 3 minus 3 to the 3rd over 3 factorial. I know you can't see this very well. Ah, dang it. I hate when I forget to go out of the exponent. So divided by 3 factorial plus 3 to the 5th over 5 factorial, and then minus 3 to the 7th over 7 factorial. Okay, so this is my approximation using my Maclaurin polynomial, which is centered at x equals 0. So I get 0.091. Okay. Now what I want to do is I want to compare that to the actual value for sine 3x. And then the actual sine of 3 times 1. So 3x, right? 3 times 1. So sine of 3 equals 0.141. So, you know, maybe not an awesome, super great approximation at x equals 1, but, you know, there you go. So now let's try it at x equals 2. Okay, so I'm using this polynomial here, plugging in a 2. So I have 3 times 2, so that's 6 minus 3 times 2, so 6 again. So 6 cubed over 3 factorial plus 6 to the 5th over 5 factorial minus 6 to the 7th over 7 factorial. So type that in our calculator. So I'm just going to go up to my previous one and change all those 3's to 6's. 6, 6, 6, 6. Okay, be careful though. Don't change that 3 factorial on accident. So here's what you should have. Sorry, that is so bright and washed out. But there you go. Okay. We get, whoa, negative 20.742. Which, I can tell you right now, when we do the sine of 6, so that'd be 3 times 2, which is 6. We are certainly not going to get that, right? Because sine has to be between negative 1 and 1. So, we get negative 0.279. So, as you can tell, at x equals 2, the approximation is absolutely terrible. Okay, so why is it so much worse at 2 than it is at x equals 1? And the reason is because this polynomial is centered at x equals 0, which means the closer you are to 0, the more accurate your approximation. So there's 2 things that will affect how accurate your approximation is. And that is how close you are to the center, and then also how many terms you use. So the more terms, the more accurate, and the closer you are to the center, the more accurate. So I've kind of run out of space here, but I guess we'll just kind of add on here. So 2 things, we're almost done here. So the closer to the center of approximation, the more accurate. And then also the more terms, the more accurate. So if I had used, you know, instead of 4 terms, if I had used 6 terms or 7 or 8 terms, the approximations at both 1 and 2 would become more accurate. So, and the important thing to remember is with sine, with infinitely many terms, if we could have, instead of just 4 terms, infinity terms, then both of these at x equals 1 and x equals 2 will be exactly accurate. But of course, it's impossible to do it infinitely many times, but that's the idea. Okay. I think that is it as far as our examples for this assignment. So what I want you to work on for this assignment to go along with day 2 of Taylor-Maclaurin polynomials is pages 13 and 14 in the packet. Okay, so let me kind of go over what you will see on pages 13 and 14. So on page 13, where it says manipulation of Taylor series centered at x equals 0. Remember, the Taylor series is centered at 0. It's called a Maclaurin series. So manipulations that can be used. We talked about these: substitution, distribution, differentiation, integration, any combination of the above. So substitution would be like for the sign 3x, where we substituted all the x's with a 3x. Distribution would be like where the whole series was multiplied by 3 or something. Then you would multiply the series, by 3. And then differentiation, integration, and a combination. So it says use the 5 series on the previous pages. So that was the sine, cosine, e to the x, 1 over 1 minus x, and natural log 1 plus x. Those are the 5 that you need to have memorized. So use those to construct a series for the following functions. So you have cosine 2x, 1 over 2 plus 2x, e to the negative 3x, x sine x squared, 1 over 1 plus x squared, and inverse tangent of x. How interesting. So, for these, let's see. I guess some tips. So for cosine 2x, you're going to compare it to cosine, obviously, and change all the x's to 2x's. So that one's fairly easy. For number 2, 1 over 2 plus 2x, the first easiest thing to do is factor out a 1/2. So it'll be 1 over 1 plus x. But the series we have memorized is not 1 over 1 plus x, it's 1 over 1 minus x. So think of that as 1/2 times 1 over 1 minus negative x. Okay, so you're going to replace, so for the series 1 over 1 minus x, you replace all the x's with the negative x, and then multiply everything by 1/2. Okay, for the e to the negative 3x, you would just use your series for e to the x and replace all the x's with negative 3x. That one's not too bad. For number 4, x sine x squared. So this has a couple things going on. We're definitely going to compare it with the sine function, but then you're going to replace all the x's with x squared, and then also multiply each term by an additional x. Kind of interesting. Okay, for the next one, 1 over 1 plus x squared. A couple ways you can do this, but probably the easiest would be to think of that as 1 over 1 minus negative x squared, and use the series 1 over 1 minus x. Then you would replace all the x's with a negative x squared. Okay. And then this last one, the inverse tangent, this is probably the trickiest, but remember, the derivative of inverse tangent is 1 over 1 plus x squared, which means inverse tangent is the integral of 1 over 1 plus x squared. Okay. Well, 1 over 1 plus x squared is sort of similar. Oh, that's what we're doing above. So take your answer for number 5 and integrate it to get your answer for number 6. Interesting. Okay, so that's what you'll do on page 13. Now let's go to page 14. So it says use a 4th degree polynomial to approximate each of the previous functions. So you do this page first. Sorry, this page over here. You get your 6 functions. Notice there's 6 on this page. And you're going to use the 4th degree polynomial And I would say for that, use 4 terms. Technically, the 4th degree polynomial means go up to x to the 4th. So for some, that might only be 2 terms. For some, that might be 5 terms. But I want you to just use 4 terms, just so we kind of keep consistent. So use the 4th degree polynomial. Plug in a 1. And then how close is the approximation to the actual? So plug in the 1 to the polynomial and then to the actual function and see how close they are. Do the same thing with the x equals 2. Plug it into the approximation, then the actual 1. And so is the error greater than the error when approximated at f of 1? So see which error is greater. I'm thinking it should always be greater at x equals 2, since that's always further away from the center of approximation. And then let's see. Here at the bottom of the page, we're starting some free response questions on pages 14, 15, and 16. You will not be assigned all of these problems, like ever. Like I'm not going to make you do all of them at any point. But let's see. This 1987 BC number 4 would be a good one to try to do. And then I would say let's also try this 1991. Man, I know these problems are old. I was born in 1987. You guys were not even a thought in your parents' minds. Okay, so truly do all of page 14. Don't worry about 15 and 16 yet. The next notes topic for series, I really need to teach you in person. So this will be the last notes video until we go back to school. I may have some more homework help videos and maybe more homework assignments depending on how long we're out. But this will be the last notes video that I'm comfortable teaching over video and not in person. Thank you so much for taking the time to watch this and copy the notes and to work on these assignments while you're gone. So I'm expecting for everyone to have worked out up to page 14 in the packet, as well as the convergence worksheet that I attached on Canvas. All right, talk to you later.